Okay, fundamentals of vibrations for single degree of freedom. So this topic is quite advanced in the sense that we have another, our department offer another graduate level class, a CE5650, dynamic of structure, which span a whole semester will focus on this structural size of dynamic problems. But here, this class, I want to touch base on this such that we can grasp the fundamental concept, which helps us to understand the structural response and also the soil response, and how to use a response spectrums to connect the dots. So I won't ask too much on this topic, but hope everyone has basic understanding. So we only spend a couple slides on this topic. So when earthquake happens, we could assume a single-story buildings like this frame over here into a single degree of freedoms. Not only limited to a single story building. Maybe we can also assume we have a soil columns. So this is soil column here. When earthquake happens, so when earthquake happens, it's kind of like upward propagating shear wave. So this is the earthquake loading as a shear wave. So same as the soils. So when this shear motions go into the structure, if we flip it like this way, so we flip it. So this is the structure or soil elements, and you are kind of apply loading here. So this will be the loading, and this loading can before we get to the random earthquake motions, we can assume this is a static force pulling your structure. So kind of a shaking this way, and then we look at sideways now, kind of have a force that pushing your system, which is now represent kind of like a pawn mass with M here. And when this being shake or this being load, we have two resistance, pretty much because of the inertia of the soil mass or the connections between the structure with the foundations. We can simplify the force that resisting the loading by a spring with a stiffness K, and also a damper to simulate the viscosity force that you may have. So if we draw a free body diagram, so this is this single mass. So this could be a structure, simple structure, or your soil columns, and your the earthquake kind of applying a loading. Now we start with a simple static load, but we walk you through getting into the dynamic loading, and more complicated will be a random earthquake loading. So you'll be loading the your mass, and what being resist to the loading is the damper. The damper is right here, and also the spring force. And the spring is equals to the spring stiffness times the displacements. So when this is loading, you create a displacement. And also the damper will the resistance force of the damper will be equals to coefficients of equivalence weakest damping constants times the velocity. So if we differentiate the time with respect to time, you got the velocity. So we have two forces. One is the internal resistance force, and one is the damping force. And we draw our equilibrium equations in the horizontal directions. So the force opposite to the directions of the Fs and Fd will be equals to mass times acceleration. So this is Newton's law, and we substitute back the unknowns right there. So this should be velocity, and we will get our equation. So this is the governing equations of structural dynamics, or the governing equations of a SDOF, single degree of freedoms of motions. So we are always come back to these equations. So that's a couple scenario when earthquake happens, or like, you know, another earthquake happens, but like there's a couple scenarios for the response of the structure or the response of the soil columns. We will look at 3 cases. The first is the undamped free vibrations. So we start from our governing equations for our structural response, and since this is undamped, so that's why the viscosity constant equal to 0. So pretty much this terms will drop out, and since this is a free vibrations, so this part you don't have any force right there, so this will be equal to 0 too. And at the initial conditions, the velocity and the displacement is equal to 0, and this governing equations will be simplified to this second order differential equations. And if we solve for this differential equations, then this will be the solutions. This will be the solutions. And then on the next slide, I walk you through how to solve like the differential equations to the solutions. So I don't want to spend too much time on this math right here, but since you have your differential equation in class, so you should be able to handle this. Let's you to figure this out. But anyway, so this is the solutions, and one important concept here is the natural circular frequency, and it related to the natural period of vibrations. So this is a very important concept that like I need you guys to understand. It would be great that if you can figure out all this math here, but I don't ask for like you know all the structural side, structural dynamic side, but this is what I need you to understand: the natural period of vibrations. So this is the time required for the undamped system to complete one cycle of free vibrations. What it means is for this like undamped free vibrations, since there's like no friction force at all, so there's no loss. So it's kind of like an ideal conditions that never happens, but the most simple form. So that's why we start with it first. So during vibrations, so this is the time, and this is the displacements. And since there's no energy loss, so when like this go on the free vibrations, there's no loss at all. So the shakings just keep forth. So it will never end with the same amplitudes. And the period between it, there will be your natural period of vibrations. So this will be your T sub n. So this is what does it mean here. And this will be related to the electro cyclic frequency, which is the reciprocal of the period. And the frequency will related to the natural circular frequency. And this frequency, it depends on the mass of your SDOF, the single degree of freedoms like systems, and also the stiffness of the resistant force, the spring force. So this is the most simple case for the undamped free vibrations. So we mentioned about the electrical period of vibrations, T sub n, and in our structural size, we have some simple calculations to try to find out this natural period of vibrations. So if you have a buildings, it's rule of thumb. It's not accurate, but like it's something as a quick estimate. The natural period of a building is equal to the number of story divided by 10. and the uniform code, building code, the IBC. So the uniform building code has a little bit more dedicated effort on trying to find out this lateral period for buildings, which is equals to a constant times the building height. So that's another way to estimate the lateral period of building. If you want very accurate results, you need like our advanced numerical analysis. For soils, there's also some like a quick way to estimate the lateral period. So it's equals to 4 times the thickness of the soils divided by the shear wave velocity. So assume if this is a homogeneous soils with one VS value, we can estimate that. So now we have some quick estimate of the soils and buildings. And the building will be building on top of the soils, and we will talk about this a little bit more later. So the worst case scenario is when your building and your foundation soils, they are in resonance, which means the period of the lateral period of soils is same as the lateral period of the building. In that case, this is the kind of like the nightmare for our engineering design, because when this happens, the building will shake in resonance with the soils. So you will expect a lot of deformations and very likely a collapse. Okay, for calculating the VS, the shear wave velocity, when the soils is not homogeneous, which means you have layers of different type of soils and of different velocity, different shear wave velocity, and the simple method we mentioned about, which try to calculate the lateral period right there, you can average the differences. So for example, you have a soil profile here, maybe you have like a 3 layers of soils, and up you have 3 different shear wave velocity. Just making this up, maybe this is 100, this will be 200, and this will be 300. So you have like a different type of shear wave velocity there with depth, and very likely in practice you get the shear wave velocity profile. You need to perform some like a geophysical field testing, and then you will have a soil profile like this: 100, 200, 300 shear wave velocity. So this is made of seconds. So if that case, you can calculate the average shear wave velocity reached by different thickness, because you may have different thickness here. Maybe this is 12 meters, this is 10 meters, this is like 16 meters. So we can plug in into these equations, taking account of the thickness of each layers until you're hitting the bedrock. Because we trying to, when earthquake happens, it come from the earth, and then the shear wave will propagate through the rock, and when you through the rock, that will be not so much changing. But when you get the soils, in soils is much plastic material than rock. Then in that case, you expect a lot of amplifications or de-amplifications of the magnitude of the shear wave, and that will affect your above ground structure. So that's why we doing the shear wave velocity profiles for the whole soil layers is essential. And the definitions between soils and rock can be defined by the shear wave velocity. So for the shear wave velocity greater than 750 meter per second, that belongs to rock. And you can calculate the average shear wave velocity with this formula. And again, this is just an estimations for layered soil systems. We need to have to conduct a soil response analysis if you want to find a more precise natural period for your soils. column. And we will talk about such response analysis at the later of the semester. When we get to module number 4, we will learn a software to get called Deep Soil. And with that, we will do like a more sophisticated analysis. For now, this is a quick estimate. So case 2, because damped field vibrations. Remember, like case 1 is the most simple case that you don't have a damper, and also is free vibrations. So when you think of free vibrations, pretty much it's like, if you have a pendulum, you kind of like take it out, you kind of like give it like a push, or like, you lift it up for certain positions, and then you let go. So the pendulums, you kind of like will be swinging freely without any like force applied to it. So that is the free vibrations. And case number 3, we will talk about like, once the structure is or the system is in free vibrations, you apply a force to that. So that would be like case number 3. But now this is free vibrations, so this terms equal to 0, but the damper, you have some damping to occur, is not 0 compared to case 1. So that's why, like this equation now, you have the middle term right here, c times the velocity, and this becomes the governing equations for this case. And there's one more terms we need to learn here now, is the critical damping. Well, again, like this is the governing equations, and the second slide shows you the solutions of these equations. So this, again, this is a second order differential equations now with 3 terms rather than just 2 terms, so things got a little bit more complicated. And I don't have the derivations here. If you want to learn more about how to get from this form to this form, I don't think our textbook cover it, but if you crack a structural dynamic textbook, you can find out the derivations. And I guarantee you'll be much complicated than this one. But like if you're very interested, I can share my course note with you. I took the structural dynamic concept when I was grad students, and I go through all those derivations. So if you want to learn more, I can show you. But anyways, so this is the equations, and this equations give us, actually, when we're solving this governing equations for different boundary values, you can have different scenario, and those scenarios are 3 different kinds. The overdamped, critically damped, and also the underdamped. And it depends on 1 parameters, which is the C sub R, the critical damping, which is 2 times M times the natural circular frequency. And the ratios of your current damping to that damping thing is this one, and then you go to the simple, the damping ratios, C over C sub R, and we know that this is the equations we learned before for the natural frequency, the natural like a period, and thus the equations can be write to this one. And again, if we solve for these equations, we will get this formula. And that's 3 different scenarios. First, critical damped, which means your damping is equals to the critical damping. So this is kind of like the so the critical damping is this equations, which is the kind of like a physical properties of your system, which means your structure. So each structure, or each like a free like a single free body systems, it has its own critical damping, because it depends on the mass and depends on the natural period. So if you know the natural frequency, If you know the lateral frequency or lateral period, and if you know the mass, then you can find the critical damping. And if it happens that the motions is equals to the critical damping, then pretty much like this magic number will make the system die down really quick. And if like your damping is greater than the critical damping ratios, then the mass will return to zero positions at much greater than the natural period. For critical damping, pretty much you'll be returns to zero positions right at the natural period. But like for your damping is less than your critical damping, which is the most case, and then you will observe the underdamped case, which the systems will kind of like oscillated in a decaying manner, like this one. So if you have a damper system in your door, when you like when you try to close the door, that could be like a critical damp or over damp the system. So it's a damper. Make sure you kind of like brakes on it. You won't like go oscillate. But if without the damper, if you just have frictions, then when you like try to close the door, you will see like go back and forth a couple times. So that's just the underdamp. So those are the mathematical representations of these equations, and the damped electrical frequency can be further described by this. Okay, damping ratio. So amplitudes of vibrations decrease with time, and the damping ratios describe the response of the structure. For buildings, the damping ratios is caused by the frictions of connections in elastic deformations. For soils, the damping ratios is caused by soil viscosity, dispersions to adjacent ground, and also in elastic hysteresis. We used to set the damping ratios at 5% for design. But why? Because steel and concrete buildings start to have architect damage at about 2 to 3%. So 5% is a little bit to the conservative side for some factor of safety chips in. So typically 5% is used for most structure design, but for some more critical structure like a nuclear plant, NRC, Nuclear Regulatory Commissions, set the damping ratios at 7%. For soils, it is very tricky. It can go up to 1 to 25%. So this graph here shows that like how the damping ratios come into effect. The higher the damping ratios, the less vibrations you can expect. Soil damping is very tricky, as the previous slide showed you. You can go from 1 to 25% because there's a great variety in soil type, from gravel to clay. This topic will come back when we talk about the seismic site response, when we try to investigate how the amplifications and de-amplifications happens in soil deposit when the seismic wave travel through it. Soil damping is a key parameters, and we spend the time to talk about how to measure the soil damping and also how to use it for site response analysis. The last case number 3, the damped force of vibrations. So now we know like in soils, the single degree freedom systems, we can simulate it as a point mass that attaches to a spring and also a damper. And we were taught for case 1 and case 2, we focus on free vibrations, pretty much like we apply displacements and kind of just like let go. So you kind of like vibrate freely with or without the damping effects. Case 3 is the case that, yes, we have the damper, and also we have kind of like a force applied for the vibrations, or alert the vibrations. And this is a force that with harmonic motions here described by the sine functions. So now this become our governing equations, become a little bit more complicated. And we reorganize the equations, kick in the electro period or electro frequency. Then this become the governing equations. And the solutions can be very complicated, because now you not only have 3 terms for the differential equations, but you also have not a constant, it's a variable on the other side of the equations. So this is the solutions, and the derivations are between to here to here. If you're interested, I can show you some math, but we're not going to spend too much time here. And again, we have graduate level class structural dynamics taught by structural faculties. We spend a lot of time to talk about this issue. So this is the governing equations, and that actually, this pretty much is the solutions. And you realize that there's like a 3 scenario here now, which talk about based on the electro period of time. So if your motions is the electro period is much greater than the electro period of the systems, pretty much this is a stiff system. So end up you don't expect too much displacements from it. At the other cases is your electro period is much less than the electro period, that become a softer systems, and the system doesn't have time to respond. And yet this is not the most scary scenario. The most terrible situations is when the electro period of your motions is about the same as the electro period of the system. At that point, we are at resonance. So in that case, this is the resonance frequency right there. And if I upload some a YouTube. I will also upload some YouTube clip on Canfax, so you can see some simple experiments for some engineers to demonstrate the effect of frequencies. And yet, the most complicated scenario is when earthquake happens. So the equations here describe the response of the structure or the point mass of the single degree freedoms systems. And when you apply to earthquake loading, so you will become random vibrations like this kind. So this is very similar to the previous case that look at, except the case number 3, we apply harmonic motions. And the damping is very important. And the earthquake is not a single frequency at a single amplitude. So the previous case number 3 is harmonic motions. You only have 1 frequency and 1 amplitude, even though it's a cyclic loading. But this will be much complicated. So that's why closed form solutions or analytical method is almost not feasible because of the capacity we are dealing with. So we need to use other numerical method to solve for the system response. And the response spectrum that we will talk about next will help on this issue.